Thanks very much, Sri. And thanks for having me come here. I haven't been to Brighton before. It's a beautiful town. Got to wander around a little bit last night. And I'm looking forward to the conference, which I haven't been to here before, and learning what you guys are doing and what your interests are. By the way, is the sound okay? Do I need to stand close to the microphone? Okay, I'll try and do that. So I'm going to be talking about haptics. I'm primarily a haptics person, and I want to take perhaps a little different approach to it than a lot of what I'm seeing going on here, although it's not completely divergent. My lab, we call it the Sensory Perception and Interaction Lab. I've been at UBC in Canada for 17 years, and before that I came through a convoluted path that began with planning to be a veterinarian, and then went to mechanical engineering and being a hardcore robotics designer, controls designer, and eventually got more interested in the people side of things and perception and eventually interaction design before I actually knew that that was a thing. And so what we work on now is a combination, there's a theme of haptics to it, especially in the robotics. I work on robotics that we touch, but a lot of other haptic things as well. But from early on, I became quite interested in how people were perceiving the sensation, not just in a perceptual sense, but what the meaning of it might be and how you could use that as a communication channel and how you would design for that. I think that my roots in engineering really made me a designer at heart. So what I'm going to cover today is that theme on design and how we design haptics for people to use and how we understand how people are making sense of it. So I feel that we're at a bit of a tipping point in haptics over the last few years. I've seen it growing maybe in the last 3 or 4 and then very sharply recently, where I got into this field. I think I'm proud to say I built one of the very, very first haptic displays in the early 90s. We didn't call it haptics then, we call it kinesthetic feedback. And it was not vibrotactile, it was forces, and it really came out of the robotics community. And since then, it's been that was a while ago. I'm dating myself. But we're at a point where actually we're seeing a lot of this in industry, and not just in expensive high-end applications, but in consumer technology. And so what I've really noticed more and more over the last 5 years especially is that designers in industry are struggling to actually use it as a design medium, and that the tools do not exist to do it. And there's a lot of actual challenges to designing with haptic feedback that's different than designing in other modalities. Many challenges that are similar, but there's also challenges that are different. And so one of the things that I've tried to do is to understand what those differences are, and then over the years we've tried to see how you would support those particular challenges that are different. So hapticians need tools, and we're at a point where tool design, I feel, is as important as the technology design because it's a primary obstacle to uptake of the technology. To generate good tools, you have to first look at what the people using those tools need to do and what their processes are and what particular kinds of challenges they go through. So I've been a researcher for quite a while, and I say I'm a designer and my students are designers. So what does haptic design look like for me? So I'm just going to flash through some pictures, and I'm sure that each one of you could show a similar bunch of pictures from your own work. I'm just trying to make a point, so I'm not going to go into it too much. We do a lot of conceptual and interaction design. You guys, especially in this room, are familiar with that. Okay, we do a lot of prototyping. Low fidelity prototyping, high fidelity prototyping. We build stuff, okay? We do experiments, and the experiments might be really elaborate and complicated and take a long time to do. We have to get them peer reviewed and subject to very high standards, and these can be quite challenging experiments that take a long time to do. And we analyze the data. And we have lots of kinds of data that we analyze, okay? So this is research, right? I call it design. This is how I design. It's pretty intensive stuff. The point is that if you're actually working in industry, all that stuff you don't have time to do, right? You can't make, maybe the prototyping, but aside from that, you're not able to do those kinds of experiments. You can't do that kind of data. You have to move a lot faster than that. This is an obstacle. If that's what it takes to actually progress in bringing the haptics into your application, it's not going to happen. And then working with haptics brings other challenges as well. So let's look a little bit at process, both for us, a research designer, but also looking at professional designers. And so we did that. We actually went out, and a few years ago, it was actually quite hard to find professional haptics designers. There weren't a lot of them. Most of them turned out to be in the automotive industry and a little bit in the surgical support industry. There's a lot more now. There's challenges because a lot of them couldn't really talk about what they did. It was proprietary. But we could talk about process to some extent and some of the challenges. And so we did a qualitative study. This was with my former student, Oliver Schneider, who's now one of those many German researchers that we're seeing listed up there. So there's lots of types of things that we do. So we tried to actually look at the stages of design. These stages are not new. They've been out there and listed in other kinds of design as well, but we wanted to actually look at them through the filter of what you're doing when you're doing haptics. So browsing, first you look for examples, you see what's out there, you get inspiration. Okay, you create. At some point you do have to make something new, and you might want to brainstorm, you might want to do this broadly, quickly, come up with lots of different designs, kind of a sketching, low fidelity prototyping stage. And then at some point you're going to have to refine, and you're going to have to share. You're going to have to get feedback from people on what you're doing. You're going to want to show it to your boss, to your client, and eventually you are going to actually have to let people try it out who might want to buy it. So let's just zoom in on one of those phases. So let's think about browsing. One problem with browsing is that if it's haptics, we don't have a common tactile design language. So far less the problem that I'm sure you can already see forward to, that you have to be physically present to actually feel a haptic sensation. We can't even talk about them. We don't even know. We don't know what the words mean or how we talk about the particular sensations. And if you're coming from an engineering standpoint, we often have our language is based on machine parameters because we're focused on actually building these things, what you tell the motor to do in order to create a particular sensation. So we have the designer who's thinking about, just using an example of vibrotactile, which is a quite restricted channel compared to force feedback even. So you're thinking of frequency, duration, amplitude, waveform, and yet we have the end user who's feeling it, and the end user might be using very different language to talk about or to perceive what that person is feeling, like urgent or musical, sounds like a motorcycle, or even just, brings to mind some piece of music that I've heard before. So there's a huge disconnect between these two ways of thinking about it. And so one of my former PhD students, also now a German researcher, this one in Stuttgart, as Dr. Hasti Seifi, started to look at it from a information visualization perspective and saying what we really need is better ways of browsing haptic feedback. Wasn't trying with this work to attack the problem that you still have to be co-located, but at least can we acknowledge that people might look at or perceive these haptic sensations through different cognitive frameworks, the same set from different directions at different times. So this is known as a faceted view in information visualization. So she made a tool called VibeViz that actually gave you access to a set from different perspectives, and actually what those perspectives were and how they were associated with each other was the subject of quite a lot of research, a whole PhD as a matter of fact. And so let's see if this works. I don't think is there sound on this one? Maybe there's not. So the idea is that you have different views that you would actually look to. This is an online web tool that you could interact with. But the point is that if you select something on one side, it's reflected in the other. So we have a physical view, a sensory emotional view, metaphor filters or usage examples, and that you could click on these different things and highlight different items in a corpus, and then you can always click on a single item and actually feel that particular sensation. So the idea is that you take a single sensation embedded in a set of 100 or so sensations, and you can see where it shows up in different maps if you're looking at it in different ways, and that can actually help you find other things. But this was simply a browsing tool. It had individual discrete sensations And what Hasti went on to do in quite a bit of other work that I can't talk about now was to say when you want to actually modify them, maybe you have two things and you want to move between them, or you want to take one and adjust it because it isn't quite what you want. How do you actually take those starting points, these examples you find in your browser, and modify them to be closer to what you want? And that was an effort for end-user customization, and we have a whole line of tools, of design tools going in that direction. So what might a detailed design tool look like? So let's shift gears and go to this another set. And I'll talk a little bit about sharing at this point, because usually throughout this, both in the early creative design and also in the detailed design, you're probably going to need to do a lot of sharing, either to get feedback or to show your colleagues or just talk about an idea and try and understand it better. So this is something that, again, back to Oliver Schneider and some other students in our lab worked on this. And so Oliver created a tool called Macaron that some of you may have run into at different conferences. We built it, it's a keyframe editor that lets you do detailed design, and I'll show you a very brief look at it. But the point is, we actually built it as a platform to study designers. So this was a tool that we took to industry designers and actually asked them to use it in different ways to design things, and then we plotted and looked at the different kinds of things they were doing and characterized their design process using it. It's not a creative tool. It's not an easy freeform sketching tool. We got those too. This one was really if you want to get precise control and do something very carefully. And we also developed a tool called HapTurk. We got very frustrated by this thing of we couldn't ever crowdsource our studies, even when we wanted very high volumes of feedback on them, because it's difficult to crowdsource haptic feedback. What we did was we actually made visual representations and auditory representations of haptic sensations, and then tested to see if we get the same kind of aesthetic responses and meaningful responses from both local and remote participants to those proxies as to the full-on sensation, so that you could actually do some kinds of studies crowdsourced. And that was HapTurk that was at CHI last year. So briefly, Macaron, just to give you an idea of what it looks like. This is Oliver's work.
The haptic libraries only let you select. Viewing the source of an example enables much more powerful tools. To study this in haptic design, we built a vibrotactile editor and added example features. We logged user actions to capture and illustrate their design process. Finding users followed an archetypal process, with examples facilitating design and helping users learn. We also report several lessons for future design tools.
So it would take a little more time to explain all the things that tool could do. It's actually a very powerful tool, but the key organizing principle of it was example use, being able to source examples and then put them together to modify and borrow them. And one of the observations that Oliver had made is that in many other design mediums, you can actually, like if you're redesigning a website or even an image, you can always go into the source and see how someone else did that, and gives you a great deal of power in being able to go and then make something different and make it be your own way. You don't have to just deal with a superficial image. And so this way of being able to open up the inside of something and expose that, take an example, open it up, and then change it was really one of the things that he was looking at. And so that tool allows you to do that as well as a lot of other things. So going back to this view, we've in no way suggesting that I've been exhausted and finished figuring out, for example, how to browse. I'll just say that we have examined the problem and have some idea of what's hard about it and what's different about it for haptics, and made some tools that let us examine that problem in a little bit more depth, and perhaps raise some challenges and say this is what you actually need to do. We have found this framework, these 4 aspects of things that people do, to be quite useful as an organizing principle. So we've looked at browsing, we've looked at sharing, we've looked at detailed editing and studied them. So I want to talk about creating now, which is actually one of the hardest things I think to do in haptic medium, because it's taking that first step in this field. When you don't, in this medium, when you don't have tools, it can be really super challenging. So a lot of our work we've done in vibrotactile because it's very accessible, it's handy to do. We can do a little bit of crowdsourcing because it's starting to be ubiquitous in certain platforms. And it is actually a lot more expressive than you might think if it's well designed. It's generally not well designed in what you see in your smartphone buzzers because people don't know how to design with it very well. And one of our big discoveries there was that affect is actually a very useful way to look at design. If you look at designing even vibrotactile feedback from an affective filter, because that's how people look at it, if you can actually design in that facet rather than in engineering facet, it gives you the power to do a lot more, much more directly. So that was great. But vibrotactile does have some limits. It is not my favorite medium. It is not what I want to be my life work, is buzzing cell phones. So let's go more deeply into affective touch as we look at creating. And the platform that we have been able to go much more deeply into for this is actually human-robot interaction, in particular affective touch. So the starting point was quite a while ago. Actually, I had a student come to me who had this thing about cats, that he had a cat. Actually, his former girlfriend had a cat, and he was quite attached to the cat. And then when the girlfriend left and the cat left, I think he missed the cat more than the girlfriend. And around that time, he came and started working in my lab, and he just said, you know, something about that cat. It's like there's touch and animals, and I think we should try and understand it more. And at the time, this was quite a while ago, and it sounded like a pretty weird thing to me, but you always have to have one of those weird things going on in your lab. And little did I know how much it would end up taking over my own work. So there is this thing where people touch animals and something goes on, and it's rather magical and mysterious, and it's very hard to study. We don't really know what it is. And there's been a lot of studies in the medical disciplines that look at how important touching animals or touching other people, how much social touch is to our health and wellness, particularly people who are vulnerable, very young, very old, very ill. Studies that show that if you've had heart surgery and you trace people's outcomes, that more important than how serious your condition was or what kind of medication you had or a number of other co-occurring conditions, what made the most difference for your recovery prospects was whether you had a cat at home. Or similar things with other animals and other conditions, cancer recovery. And so it's very high level. Like, you have a cat. What are you doing with the cat that is so important? Is it that you have to care for the cat and you're responsible for it? Is that it looks at you in a wonderful way? Is it that when you walk your dog that you're socializing with other people, because that's also known to have happened? Or how much is it that you're touching it and it's touching you, and that this is somehow activating something very primal in us that would be good to understand better. It's very hard to study. We can't control the animals. It's a difficult area to study. So we set off to try and study it with a robot, and built a robot that would actually start to break this down and look at it and see if we could see what was going on when people touch animals in a more controlled and sensed way. So it really started as a platform for studying emotional touch. And this was a very simple model that Steve Yohannan, the student of the cat, came up with long ago. And it almost seems so simple that it's hard to, why even bother writing it down? Okay, so the idea here is that you have your person on this side, the robot on that side. So the person does something, touches perhaps, but usually you touch with some kind of an emotional intent. I don't touch a cat the same way I would touch this object necessarily. I would touch it with, I'm going to pet it, I'm going to tell it something, I'm going to somehow have some social or emotional intent in touching it. It's an emotionally evocative thing that I'm going to interact with. Okay, and then the robot then has sensors on it and perceives the touch in some way. And there's a step of perceiving, which is just, oh, I was touched in a particular way, what the sensors tell you. And then there's interpreting. What does that touch mean in terms of what the person meant? So there's now some user modeling going on. And then how is the robot going to react to that? So am I going to respond in a pleasing way? Am I going to get all revved up and playful? What kind of fuzzy robot creature am I, and how am I going to respond to that? And there's an aspect of personality or even agenda in there in terms of setting the personality. Okay, and then somehow I have to render that. I'm the robot, I need to show my response in a particular way, and this of course depends partly on what I can do, what my degrees of freedom are, and what I'm able to move and what I'm able to show, but partly on, again, my personality and how I choose as a robot to behave, or how my program tells me to do that. Okay, and then we're back to person, and person is perceiving this, perhaps through their hand, or if they're hugging it, their body in some way. And somehow, and then you do exactly the same thing on the human side. The human perceives it, interprets it, and then decides how they're going to respond. And you could substitute a real animal in here, robot, but there's interactive loop is going on. Now, if we're looking at it as a robot, then you can quickly see we have some work to do. We're going to have to do some sensing, we're going to have to do some recognition, we're going to have to do some user modeling, and vice versa. We're going to have to design a robot that can move in interesting, expressive ways, and we're going to have to be able to run a program that can do all of this. And so Steve spent a lot of time working on these two kind of engineering challenges. But also, we have this idea that eventually, if you close this loop, what's going on in the human? Can you actually change the human's emotional state? And this would be very interesting if you could do that, because then, of course, you're having something that looks a lot like what happens with animals, but you're doing it with a robot. And then you know that maybe there's something going on with real animals that is rather mechanical, because you can replace it with a robot, which is not a real thing. So if you put these things back together, is there a synergy? And these were really the defining research questions that we had initially for this project that we set on. So there was about 5 years of work, which roughly coincides with Steve Johannen's PhD thesis. This is the robot that he built. It was not the first version. He made a few passes at it before we got even this far. And you can see it was using technology that we could put together around 2011 and so forth, and the possibilities for surface touch sensing were not at all what we have today. We had to make do with, I say that this is our turtle with a fur coat. It's fiberglass with force-sensitive resistors on it, which worked better than you might think. It looks pretty awful. It doesn't feel right, and there's all these gaps in between the sensors where you can't sense anything. But we actually could get some touch sensing off of this. We needed pressure. We knew right away that we needed pressure, not just surface touching. And it could move in some particular ways that we did a great deal of pilot work to figure out, using various kinds of puppets to try and understand what people were considering as emotionally expressive motions. And so you come up with something that we figured that the breathing seemed to be fairly important, but it could do things with its ears. It could purr. We tried heat for a while. The problem with heat is this thing is full of motors, and we are just desperately trying to dump heat out of it because you have all these big, strong motors inside a fur coat, and we really didn't want to add more heat to that system, so it was burning out motors pretty badly as it was already. So it's warm, trust me. So we used this platform, and we did a few things with it. So called this the Creature 1.0. So there was 3 primary questions that align quite well with that model that I showed you. So you start by saying, how do people interpret the creature's emotion rendering? In other words, when it moves, what do people think it's expressing? How do people display particular emotions to it? So that we were hoping maybe that if people made very characteristic ways of interacting to show emotions, you could figure out what their emotional state is by looking at their gestures. If you could actually sense that, then you would have that would be really nice and clean. Okay, and then do people's emotions move when the loop is closed? And I'll just give you the short answer that yes, they do. I'm not going to tell you about this whole long study we did. That was actually another student past Steve who was able to document that quite strongly, and not even with kids. We thought that this would be a platform more effectively on kids, but it works on adults very, very directly as well. So there's a bunch of papers here where we talk about these things. And I'm just going to give some high-level overview of the kinds of things that came out of it, because this is, again, work we did a while ago. First of all, just to get me situated, who is familiar with a two-dimensional model of emotion or affect? So most of you. Okay, so I don't have to go and you see a lot of arousal and valence in here, but you guys know about that. So here's first of all, something we called the Touch Dictionary, which Steve generated by having a whole lot of people talk about and demonstrate how they would express particular emotions to this fuzzy robot. Okay, and what we came up with is so this was qualitative study. where we came up with a lot of particular emotions and definitions of how people would do it, and we confirmed these by going back to people again and asking people to confirm them and then demonstrate them again. So we felt a pretty strong validated thing that probably applies quite well to animals as well as a fuzzy robot. I'll come back and refer to that touch dictionary again. One thing that I just won't go into too much detail on is that we also did some other studies where we looked at the frequency with which people used these gestures to display particular emotions, hoping that we would see some kind of rough correspondence so that we could use gesture recognition to infer emotional state. And I'll tell you that that works occasionally. There's a few things that people use very characteristically and definitely. For example, distressed. If you say, show that you're distressed, people will usually do the same thing, which is they'll pick the robot up and hug it. Okay? But if you ask them to show almost any other emotion, they will do a whole bunch of different things. And so this idea of being able to say, oh, if I see a particular kind of stroke or something that means a particular emotion, this one-to-one mapping, was clearly not going to happen. But what we did see was that when people were expressing different emotions, they would make particular gestures, but in different ways. And we could see this in video studies, because remember, our touch sensors were really not up to snuff right now. We couldn't detect what people were doing with the resolution that we really wanted. But what we could do is we watched them and we could see, and we had a very strong suspicion that there was actually a lot of differences in the way people would modify the touches they were making depending on their emotional state. And so if we had better touch sensors, we thought we could actually do better, not looking at which gesture they were making, but how they were making the gesture. So we come back to this thing later. My computer is frantically telling me to reconnect to wireless network here, so hopefully that's not interfering. So anyway, life moved on. During this period, a lot of people came through our lab and would see this robot, and as inadequate as we felt it was, this funny platform that we had intentionally, I didn't really talk much about the design of the robot itself, but we intentionally designed it to not look real. It's not representation of any particular animal. It's very just a fuzzy mammal that maybe vaguely brings to mind a few different kinds of animals, but no one in particular, but mammals, so people have some expectations for how it should behave. It doesn't have a face, it doesn't have eyes. All those things were very intentional. I won't go into those decisions right now. But it was designed to be a platform to study emotion in the context of an affect grid. Okay, like can we be recognizable on these 4 places? But as people came through, seeing the robot, and were intrigued by it and said, oh, like I have an autistic kid and I think that this would really be great for their therapy, or someone who studies chronic pain and felt that this would have potential there. There was many people coming through who were saying, this has therapeutic potential and you really need to look at that particular application. So let's go on record, it was not my idea. But so when we looked at that concept, we really needed interaction design. We needed to not just have this object which could render in one particular static emotional thing. It had to have a story. It had to have a narrative. And to the extent we started working with kids, kids always needed a story about the robot. They needed to know what its origin story was, what it meant when you turn the power off. Was it dead or was it asleep? We got very careful about turning power off. This version had a tether. Its tail actually had data and power, so it had to go into the wall, and that generated a lot of questions from the kids. The kids knew it was a robot. There was not confusion about that. But they needed to know more about it, and they were really ready to put their own story on it, but either we gave a story or they had to come up with a story. There had to be a story one way or another. So this idea of narrative frame is something that we've studied quite a bit more recently, trying to get deeper into that. But people need to have a story about the robot in order to interpret what it is and what I'm doing with it. So when we decided to start going into these therapeutic applications, we needed to design a robot that could support a larger interaction and that could move dynamically. I don't mean move around physically, but could actually progress the story and not just do one thing and then switch to another thing. And so we needed a different robot. We needed a robot, for example, that could do an orienting response. It could be, now we're more concerned about visual gesture as well as what you feel, because when the person first encounter the robot, they won't be holding it. A scenario that was very helpful for us to work this out was one that we were working in at the time, which was, I can tell stories about studies until I'm blue in the face, but one thing I will tell you, we found that the robot had a very strong effect in calming people down. We first tried to study this in kids, but we found an experimental problem right away, which was that to study calming kids down, you have to start with them being upset. And that meant we had to get them upset, and this turned out to be ethically problematic. And so we tried a lot of different things. Like there was a school near us that has kids with learning disorders, and as part of their daily routine, they actually put the kids in somewhat stressful situations, and we tried to piggyback on that. But all we succeeded in doing was putting them into a flow state rather than calming them down. It was actually very hard to experiment with the kids because they were too intrigued by the robot and wouldn't settle down and just let it be in the background. So we ended up working with adults a little bit more, but we continued to look for contexts where we could study upset kids, and it came to me without any effort when an anesthesiologist asked if they could actually put these robots into the waiting room of kids who were about to go under major surgery. We had kids that were already stressed out and needed to be calm when they went into the operating room so that the anesthesiologist didn't have to basically struggle with them, because that generates really bad outcomes all the way down. So, and they wanted something that was non-pharmaceutical, and so they thought a robot could be great. And so we started actually trying to figure out how that would work in a preoperative setting where you have kids, and a kid is coming in, the family is stressed out as well, and you want to actually design an encounter with the robot where they come in and they see the robot. We need a story. Okay, what's going on with the robot? The robot is sitting on a table or it's sitting in a basket. The robot is scared. You need to pick it up, and you need to take the pill, which is you need to hold the robot and get the robot close to you so that we can deliver what it does to you. So we had to construct a story and support that. So what do you need? An orienting response. You need to see that the robot is paying attention to you. You need to be the robot needs to show that it's frightened and scared and huddle versus I'm great, I'm open and good for business, I'm feeling playful. So you need to be able to do that. A lean in, you need to be able to lean its head against you and cuddle. You still need to do all the affect grid stuff, the arousal and valence, and it needs to be clinically robust, and that one was not easy. We're thinking about kids throwing up all over it, like we need to be able to handle that. So I thought, oh, this is not another 5-year computer science student trying to build a robot. We need to go to a professional design firm for this. So we did, and this is what resulted. And I can say that it did not work out. And the reason was that the design firm felt that our piddly $200,000 was not enough to really do the kind of design that I wanted, which would be iterative and doing a lot of wide-ranging brainstorming about how you could actually implement these different functionalities. They wanted engineering specifications and then to go and build them. And it's kind of hard to, right off the bat, give an engineering specification for lean in and feel cuddly. You know, it's like it takes a little while to translate that. Or this whole thing about shrinking away versus being relaxed. You know, this is not something that you get right on the first pass. So we figured out some useful things in terms of how to do something modular. 3D printing had happened, so we could make a platform that we could keep modifying and changing the outside. But there was many things that just didn't work, and I have to say that this was a very expensive lesson, and we haven't used this robot for a single study yet. But we did learn that we needed better physical editing systems. And so student Paul Bucci, for his master's degree, actually starting for his undergrad, he's now my PhD student, started developing, and he actually came from a visual arts background and started taking very seriously this haptic sketching thing. And he developed these design systems where we decided to focus on 1 degree of freedom, breathing initially, to say, let's really understand breathing, and let's make a whole bunch of very simple, quick to iterate robots and just design the hell out of that. So we went the opposite direction of the very expensive one-off robot and developed these modifiable template systems. We came up eventually after a lot of work, came up with 2 that we then did a lot more work on. Just to give you an idea of what that looked like. This was presented at CHI just earlier this year. I think that there's no sound on this one. So this is just showing design process, and I think from the look at the demos and things that you guys are not going to be too shocked by this particular approach to design. I think that the engineers who built our Cuttlebot, we're not thinking along these lines. So we start very simple. We're trying to say, well, how could you make breathing work in a way? And we were very interested in the robust thing. We wanted to be able to throw it at the wall or step on it and have it not break. It should never burn out. We want kids to be able to look at this and not feel like it's super delicate. We looked at eventually two different families. We were interested in contrasting whether if you have something kind of ribby and hard, how people would react to that compared to something soft and fluffy. So we came up with two very different design ethics. We called them FlexiBit and Ribbit as the two different approaches. Both of them have a very similar basic idea, which is there's internal compliance in the structure, and then you have a motor inside that pulls on it. That way you can squash it and it doesn't break the motor because there's nothing to backdrive. It's a tendon driven. And and then you have to cover this with fur for it to be very nice to touch. But then you can get this remarkably expressive motion just from this breathing thing where you can actually control. Remember, it's not just up and down, but you can change the rate, the roughness of it, the symmetry. And all of this is quite controllable. So we went on from there and say, how expressive were these robots actually? And so this is a study. We've done lots of studies with these things, but I'll just try and run through one. So this is showing 14 subjects who went through and rated the robots, how well they achieve particular emotional things. So the top row, so these are not laid out on an affect grid, but each one individually is an affect grid. So we have valence across the top and arousal on the bottom. And the circle is kind of, just think of the centroid of where subjects found it to be. And the big green circle is standard deviation kind of stuff. And so what we're basically saying is if you're right in the middle, what you're saying is that this would be neutral valence, neutral arousal, like not super low of either one. So what we're trying to do, you look at this row, it's sluggish, droopy, bored, drowsy. What we're trying to achieve here is low arousal and negative valence, okay? You see that? Those are low energy, but not particular positive, okay? So we would expect to see something on this side, valence-wise, and in the bottom, arousal-wise. So you want to see something in this quadrant. Not too good. Okay, we didn't do that one too well. But if you go on, you see, here we are trying to achieve calm, relaxed, serene, at ease, which this would again be low arousal, but positive valence. And you can see that worked a lot better. We got our quadrant. We got the low arousal and positive valence pretty well. So okay, we did that better with these Cuttlebits. And then we tried to do attentive, proud, enthusiastic, determined. So there you have high arousal, positive valence. And we say, well, it's a little bit mixed here. We generally, this is the one that's closest to being in the right quadrant. Okay, and then finally, we have guilty, hostile, nervous, and scared. Once again, we got arousal pretty well, but valence, not so much. Okay, so there's two that we actually nailed pretty well for that. But if you look a little bit closer, what I've highlighted here is whether we got half of it right. Okay, so in this case, we can see that we actually got arousal correct. So where I've highlighted it, the users actually perceived arousal the way we intended them to. By the way we generated these behaviors was by working with other subjects to generate them. We went back to new subjects and saw how they perceived them. So here we got, for example, arousal was always correct, always correct, always correct, and almost always correct. So basically you say we did well at arousal. We could generally get arousal in either direction. What we could not do was valence nearly as well. We're not the only ones who have this problem. Generally, valence is much harder to predict. You can tell if a dog is wagging its tail, is a classic example. Is the dog wagging its tail because it's furious and excited, or is it happy to see you and excited? You might actually, even if you're a dog person, you might not be able to tell. You might have to know that specific dog to be able to interpret that particular thing. And I will point out that the Cuttlebits do not have fangs. So it's actually kind of hard to access that particular dimension with these robots. So that could tell you, oh, what do we have to do in order to be able to go there? But I want to move on from there. That gave us feedback about what we needed as we continue to design this, and we're going on to design other degrees of freedom, for example, that hunch thing, and try and integrate it with breathing. But even when the body is adequate, it's very difficult to source the movement. And so we've done a lot on that. And now we're getting back into that create thing. So we've done create in terms of being able to generate lots of body templates. It was hard to do that. That was not quick prototyping, but now we have a system within which you can rapidly prototype. So it's become a prototyping design tool that you can modify things. Now we have to source the behavior. What should they do? And we actually observed that when we asked people to talk about, how should it show something, people would be at a loss for words, and they would start vocalizing, nonverbal vocalizations. They would start making sounds like, oh, it should be angry, or it's tickling, I want to tickle it, and making things like that. So we finally said, well, why don't we just take the sounds they're making and see if we can do that a little bit more directly. And so this actually came out with a much earlier idea that Oliver had. This is a sketch from way earlier on, where he thought, wouldn't it be cool if you could actually, he was thinking about examples, if you could just source examples from different places, like holding up your microphone to just some sound that you thought was kind of interesting, and then source another sound, and then be able to move a slider between them to kind of get the qualities that you wanted. That was an early inspiration that we have since built that for a number of things. But that sourcing part, we thought, this is Voodle, which we presented at DIS earlier this year, and I understand that someone in the audience has already seen it. And then a Mac mix tool was that macaron mix that I showed you earlier. We adapted that to be able to do this mixing thing with examples. I won't be talking about that. But here is Voodle.
We present vocal doodling for effective robot interaction. When describing something abstract like motion, many people may find themselves at a loss for words, and may opt to use non-word vocalizations to express themselves. Voodle translates the properties of your voice into motion on a 1 degree of freedom robot. Voodle detects features like pitch and amplitude and interprets them according to a set of user-definable parameters. With Voodle, users can quickly and naturally sketch effective behaviors in a unique conversational design space.
So I had the pleasure of being the one to demonstrate Voodle at a haptics conference about a year ago. And I now know that I can sort everyone in the world into 2 categories: people who are willing to bark at a robot in a public setting, and those who are not willing to do such a thing. So how expressive was Voodle? And so that thing about self-consciousness, we actually did a study. We decided to use professional voice actors because that inhibition thing was, not everyone was willing to do this. And so this is some data that we actually found where people, we took 3 voice actors over 3 sessions and asked them to sketch on an affect grid how expressively they thought they could design with this platform. And so this was session, these are our participants. And you see in the first session, they kind of weren't, this is where they could achieve something, and then progressively they would draw more and more. Now in between these sessions, they asked for improvements. They asked for different bots, different cuddle bits. So we would go back and do new robots, and they would ask for different things on the Voodle tool, so that we could actually, I want different things. I want more reverb. I want to be able to control these different things on the tool. Remember, it's not directly going from your voice to the motion. We actually run all these filters on your voice to actually pull out different things, and then have a control panel where we can adjust the filters. So people would ask for that. So the tool is actually fairly sophisticated in that way. And so you can see that by the end, people were able to do a lot more. And we have to chalk this up partly to experience in working with the medium, but also to improvements in the tool as we went along. So anyway, I'm getting close to the end here, but I've been talking about the robot display. But remember that it was very important to be able to sense the affective input, and this is actually some really cool work that we've done a lot of in our lab that I just wanted to talk on, especially given this conference. Sensing and recognizing affective touch. So this is our very first, not our very first, but one of our most fun early examples, satisfying ones. So this is the work of Anna Flagg that was done as a live demo at a Haptics conference in 2012. And what it actually consists of, it's purely a fur sensor. So we actually had threads interlaced into the fur. And the way it works is that when you squiggle the conductive threads together and they touch each other, there's a stochastic signal that changes in ways that you can do really cool things with machine learning on it and actually be able to accurately classify a lot of those touch gestures from Steve Johannen's Touch Dictionary from way back. So it is a kind of a really surprisingly effective thing. Now, the devil was in the details. It actually was not that easy to make these things. You have to get lots of parameters adjusted quite right. And it's a little bit washable, but we weren't so sure about the kids throwing up on it, okay? So we ended up also looking at other sensors that were more, and remember now this is moving past, this was now still, I think this was done in 2011 and 2012, and we were still in the shape of having to invent our own touch sensors. There's not nearly as much work as there is now. And I just wanted something I could saran wrap an object with and have relatively low resolution touch sensing, but completely flexible, like fabric. I wanted to tailor something. And I didn't want to have it be on a hard surface. It should be a squishy thing. It should feel right, no more turtles. And we just needed to find a way to do that. And I wasn't willing to put up with fiberglass and FSRs anymore. What's going on there? Okay, so we did a more extensive study with a sensor that I'll show a better picture of in a moment, where we were able to classify these 9 gestures pretty accurately. And this is how accurate they were. So essentially 100% classification of those gestures I showed you were the most frequently used gestures in our very large touch dictionary. So if you could do those, you're doing pretty well. Again, this is just telling how people are touching something. And what was a surprise, though, that we completely didn't expect, was that we could tell apart person. Like, you could tell which gesture they could make. You could also tell which person was making that gesture. And so I said, wow, so you have a little robot, and it's in the family or in the classroom. You could tell if it's Johnny or Jane who's playing with it right now, and it could actually respond in a personalized way to them. That's very interesting. So it tells us that people are touching idiosyncratically, but also differently, but also these gestures are very easy to determine, even with a very, very simple, low-cost sensor. So this is the sensor. This is not the first sensor. This is a simple one. It's made out of electrically striped fabric with a separating layer. So basically, it makes these pixels or taxels that are about 1 centimeter in diameter, the current version we're using, so that it's about the size of your finger, and this is all the resolution we need for the kinds of gestures we're making. If you have more than that, it's just extra computational load and more wires you have to deal with. And so you could take this and you can tailor it and you can put it on our little fuzzy cuddle bits or under the fur, and it works through the fur and it works without, it doesn't have to be against a rigid surface. So we could actually do pretty good touch sensing with pressure on this particular platform. And so what did we do with that? So we've done a lot, and I'm not going to have time to talk about it all, but we are now at the point of actually being able to infer emotion as well as what gesture you're making from the way people touch to some degree. And there's a study here that I will just briefly touch on that we recently finished, where we're actually comparing what we could do with just touch with biometric input, which is currently probably the gold standard for affective sensing, and we're now moving on to using EEG as well as a gold standard comparison set. And we're finding that touch is not as good as biometrics, but it's not bad either. You can actually tell a lot. But the most important output of this study was that this whole idea of the affect grid, we're starting to kind of say it's not very useful for us anymore. Saying emotions are static, no, emotions are dynamic, you're having multiple emotions at once. And it's too high a standard to say we're going to label your emotion right now. Instead, we're going to look at emotions change over time, and it's a dialogue. And we're going to make guesses and then respond and see if that's consistent and narrow down our understanding of what emotion you are in right now. And this is really a more realistic way and more naturalistic way of how it works, because this is how people determine each other's emotions. If I walk into the kitchen in the morning and my husband makes a joke, how I'm going to respond to that joke might depend on what mood I think he's in. Is he making a joke, or is he serious when he said that thing? And I might have to probe and kind of follow up and check and see how he responds to my follow-up. And so that's the way we work as social animals, and so we're looking more at that. But there's another problem here, which is all of the studies that I've shown you so far, or most of them, we had to ask people to pretend to simulate emotions, and we really wanted a situation where we're accessing genuine emotions and we knew what they were. So we actually because obviously we need more certainty that we were after the right thing. So we developed a whole new experimental protocol, now working with emotion psychologists, where we asked people to come in and think about strong emotion experiences that they had, so memories, and then to actually tell these stories to the robot, okay, in a private room with a camera on their face, but no sound, so that they could speak or not speak, but they would not be recorded, audio recorded, for privacy's sake. So this is, speaking of twisted setups, I would not have been able to think, this is my students, Laura and Paul did this. You can see the evil grin right there. So it looked a little bit contorted, comfortable chair, but the person is holding this. We're also looking at gaze as another biometric, another modality. They had the biometric sensors on them, and we were really looking at how this compared with their biometrics. And so each participant recalled a strong emotional experience, and they could only go through this twice. It was pretty involved. They had to tell a story, and we gave them 2 conditions, and it worked a little too well. There were tears. We actually stopped the study because we were afraid that we shouldn't be doing this without a psychologist present. It seemed a little bit off to put someone to tears into an experiment and then say, oh, thank you very much, and here's your $10 and go away. So, but we got some great data. And so we asked the individuals to report the genuineness of their movement on the affect grid. So basically, where did they start? They started from a relatively neutral point, and we saw that for each of these, they had a lot of movement from neutral to the outer edges of the corner. So this is just confirmation that, yes, they self-reported that they experienced a change in emotion that was genuine and quite substantial. And we visually confirmed this. It was very evident. And so I have a data view, but it's not very easy to explain, so I won't show it. Basically, what we saw is that biometrics got this 100%, touch got it pretty well, gaze not so much. But like I said earlier, the really interesting part was that we're now looking at, because people were telling stories, there was this journey that their touches went. So we have this rich data set where people are touching it and things are changing as we go. And we're now mining that data set and collecting more data set to really look at this dynamic model of emotional touch and upgrading our sensors and all of that so we can actually to see more of what we're actually looking at. And a lot of this is computational and just how fast we have to be sampling and how you deal with the huge volumes of data that you're coming up with. So, and then moving on to these interactive scenarios where we're actually deliberately trying to modify people's emotional state. So I'll stop there. We're going on and continuing in these therapeutic directions. We've deconstructed the design process to understand what's different about design, requirements for tools. We've made a few tools. We've posted all our tools online. They're all available. And mechanisms to evaluate haptic design closer to scale and trying to figure out how to do that, but there's lots more to do. I just wanted to give a really quick plug. Sri mentioned that, not my personal lab, but a large initiative across UBC that I'm leading called the Designing for People Research Initiative. We are recruiting for graduate students for a big graduate training program that we're launching. We just launched this fall, so you apply now for next fall. So if you're interested in something like that, it's a really cool program, and I can tell you all about it. And this is what beaches look like in BC. So I just have to say that. Okay, so, and I will stop there.
That was amazing. Thank you so much. I'm really particularly interested in what you said about how the Cuddlebot doesn't have fangs. And so if you think about like the real cat, like cats are haughty and they go off halfway through and they leave you, but people form very strong emotional attachments to them. And I wonder what your thoughts are on how much it's necessary to build, if you're building like a robotic approximation of a living thing like that, how much it's necessary to build in the fangs or the rejection or the kind of that, the more negative emotions as well, to make it a really kind of rich emotional integration that people have with it.
I think it's really important. Maybe not fangs. The fangs joke came about because we were worried about kids actually breaking the robot. To tell them it's inappropriate. But actually, there's a lot of conversation in our lab about sustainable interaction, so going beyond the one-off and actually building up a relationship. There's been lots of robot toys. Aibo is an example that everyone's heard of, the little Sony dog. Incredibly cute, way more capable robot. These are simple robots. They don't do very much. But my belief is that going after the goal of making something that's as enticing as a dog or a cat, and that richness is that people can work on that. It's going to take a long time. I love animals. We're so far from being able to do that. What I'm going for is more something that's in the background, but it has to have some of those qualities. If you take a kid with their stuffy, it doesn't do anything, and yet people form these very, very rich relationships with them. What we are trying to do is add just enough so that people put their own story on it and bring most of that interest to it themselves. It's not going to be exciting, but it needs to be something. So there needs to be some expressive palette, and I think of some of the things we've put a lot of work into figuring out. So what does it need to do? And I think that I'm feeling good, I'm feeling bad, and also acceptance, rejection. Go away, I don't like it. I don't like the way you're touching me, you're going to have to do better than that, like a cat would do. Versus, oh yeah, you need to be able to do that much. And so I think that that's important. The hostility and the anger might be appropriate in some cases. When I'm working with kids, it's kind of an open question of whether you actually really want to be doing that or not. But there has to be something. Our robots can't run away. And that's really importantly different from a cat or a dog, because a cat will show its displeasure by leaving, and we don't have that with these robots. But I think that there are a few simple things that the robot has to do for it to be rich and sustained and actually keep you coming back and getting something